Okay, so today we're going to look at exploring, or they called it exploring or traveling through the network. So obviously we've got networks which have vertices and the edges. And generally, as I said, networks are often known as a directed graph. And so we have different pathways or different things, ways we can go through it. And they all have different types of names. And so you will need to remember these, and or you might need to refer back to this summary page when they maybe ask you what type of path or thing is this. All right, so the first one we're going to look at is a walk. Okay, so a walk is a sequence of edges, so you move along the edges, linking successive vertices. So that means the next vertex after the next, like that has an edge in between them. And so they've done an example over there. So when they write out, you can see they've written out the example. That's how you write, they said write out a walk. That's how you write it. So what they're saying there when they write that A, that I'm going to start at A and I'll go along the edge to C, which I'm doing there. And then I've gone back to A. So we might see some little arrows. You might put some arrows in there as well because it's gone back on itself. And then from A, we've gone to D, and then D, we've gone to G. So we might put the little arrows in there. So with a walk can have repeated vertices. So you can see I went to A twice, and I also used the edge between A and C twice. So the thing is, you can have repeated vertices and edges. So maybe the point to write in there that this one, a walk, has no restrictions. So you can pretty much, just keep going around and doing whatever. That would be a walk. So to be honest, like most things, even when you get a restriction, is a walk. Yeah, because it's like the basic one, So most things could originally be described as a walk, but then we get into a little bit more detail. So the next one we're going to look at is a trail. A trail. So a trail is a walk, which I told you. So a walk is pretty much going to be a lot of things. So a trail is a walk that with no repeated edges. So that's the important thing, no repeated edges. So so if we go and do that walk over here that they've said, the trail, we're going to start at B, and we go to E, then we go to F, then we go to C, then we went back to B, but I've gone to B twice, but I haven't used an edge, and then I've gone back to A. So we probably would make a little note there that, the vertex B was used, vertex B was repeated. So you can repeat the vertex, you just can't repeat the edge, okay? So the next one that we're going to look at, so that's a trail, so no repeated edges. And the next one we're going to look at is a path. So a path is a trail. So a trail, remember, has no repeated edges, but it also has no repeated vertices. So we're not going, so the one above, because we went to B twice, it couldn't be a trail. So no repeated vertices. So we might want to write in there as well, no repeated edges, because it just said it was a trail. So no repeated edges either. Yeah. And so if we go and do their example there, so we went from A to D to C to F to E to B. Okay, so I haven't repeated a vertex, I haven't gone to a vertex twice, and I haven't gone over an edge twice. So that's a path. Okay. And then we got a circuit. So a circuit is a closed trail. So remember, a trail has no repeated edges. So we're not going to go over it twice. We can go over the same vertex, and what you'll see is the ends. So a trail that has the ends the same, start and end the same vertex. So if you have a look, see how A and A are there? So that's what they're talking about. So if we did that little one for a practice, so we went A to C, C to F, F to G, G to D, D to C, D to B, and then back to A. So maybe you might want to put the little arrows in on your diagram as well. So A to C like that. So you can see we didn't repeat an edge, but remember a trail you can go to the same vertex more than once. And if it's a circuit, you're going to end back at the same one you started at. So that's pretty self-explanatory. Hopefully you can realize a circuit, you know, like in a, I don't know, if you did any electrical, you know a circuit has to be closed, yeah? So you close it off. All right, and then the last one we're going to look at is a cycle. So a cycle is a closed path. So remember, a path doesn't have any repeated edges, so no repeated edges and no repeated vertices. So that is a cycle. So except for the last one, so except for the apart from the start and the end vertex. So a cycle, see how F and F, that's the only one that is technically repeated in a cycle. So we've got the example there. We went from F to E to B to C and back to F. So that was your little cycle. So you just have to, it takes a little while, and you probably need your little summary sheet next to you while you're practicing this and doing this chapter. It'll help you hopefully click in a bit, because obviously knowing them a bit more, being very familiar with it, will make you quicker. So this is just a little summary of just what we talked about. So if we look at it, a walk can have any amount of edges and vertices, and it's all just sort of, you're just linking it together. You don't come off your page and you just draw around. If we look at a trail is a walk with no repeated edges. Then we had a path, and a path had no repeated edges or no repeated vertices. The next we had a circuit, which had no repeated edges and the start and end same vertex. And then finally a cycle. Oops, sorry. A cycle. A cycle that had no repeated edges and no repeated vertices, except for the start and end the same. All right. Okay, so we now are going to talk about a Eulerian trail. So remember, if we think about the trail had no repeated edges. So if we go through this, so a Eulerian trail, or I don't even know how to say it with the right way. So it uses, a Eulerian trail, it uses every edge in the network. Now, a trail, you only use an edge once. So when you have a Eulerian trail, it means we're going to use every edge in that network, but only once, and we're going to go around it. So every edge exactly once is a Eulerian trail. So for a Euler trail to exist, all vertices must have an even degree. So what do we mean by even degree? That means so the degree would equal, say, 2, 4, 6, etc. That's what they mean by even, all right? And there must be exactly only 2 even. So you either have all of them even, or you have only 2 even and the rest are odd. So if you want to just remind yourself, like odd degree, they're the odd numbers, yeah? Would be something like 1, 3, 5, etc. Just so you're reminding them. Okay, so if the degrees of all vertices are even, start with any vertex in this case, and then in the case of starting the vertex and ending at the same. Okay? So that means if they're all even, you should be able to just start anywhere. If you have two vertices whose degree is an odd number, I think that's supposed to be even. Oh, sorry. If you've got the two odd and all the rest are even, you then start at one of the odd ones and work through it. Okay. So, and you will end at the other odd vertex. So let's have a look at this one. So it says, if you look through, they've labelled all the, we've labelled all the degrees. So you can see here's the degrees of all the vertices. Okay. And so we can see we have two vertices that have odd degrees. Vertex, they're not the degrees. Yeah, sorry, they're the vertices. They're the labels. I'm just going to do that, okay? Sorry. This is confusing, this one, because they called them that, all right? So let's go and find the degrees of this one. If we have a look at vertex 3, what would its degree be? It'll be degree of 3. Yeah, what's the degree of this one? Degree is 2. This one is? Degree is 2. This one is? Degree of 3. And this one is degree of 2. So what we're going to do, if we're going to do a Euler trail, we're going to, because we've got two odds, we're going to start at the odd and go through. So if you have a look, they started along the D line. They're calling the edges a letter. So they went D, E, C, A, B, and F. And you can see I ended up back at the same vertex. Sorry, I never repeated an edge, but I did go back to a vertex twice. All right, so then if you look at the other options, they started at, if we start at B, so start at one of these vertices. Possible Euler trails include. So B, you can still see, if I did this line, I'm going to do it in pink. So if I did this path, you can see I'm going along B. I still started at that odd degree one. So B, A, C, what did they then want to do? F, D, and E. And you can see I still ended back at the other odd one. And then if I did this one, you can see I'm going along the odd one, starting at the odd vertex of 5 and going up A, B, what do they do then? D, F, and then back up. All right. So that was now we're going to look at a Eulerian circuit. So remember, a Eulerian circuit would not repeat an edge. So see how Eulerian starts with E? So you can remember it's an edges one. So it means you only use the edge exactly once. And a circuit means you're going to start and finish at the same vertex. And because it's Eulerian circuit, we're going to use every edge in the network. So we use every edge exactly once and starting and ending at the same vertice. Yeah? So, so when this is possible, all vertices are of even degree. So let's go and write the degrees of, they've done it again, sorry. The degrees of these vertex. So this number 1, let's just, first of all, let's just put circles around our vertex so that you're not confused, okay? That's their label. We will normally call them letters, okay? So now when I go to do the degree of 1, that has a 2, a degree of 2. 4 has a degree of 2, 2 has a degree of 4, 3 has a degree of 4, 9 is 2, 8 is 2, 7 is 2, 5 is 2, this one's 4, and this one's 4. So you can see they're all even. And so it doesn't matter where you start, you'll get through it all and you'll start and end at the same. So if I went through with my highlighter and did what they said start at they started at vertex 1, they went to 2, they went to 4, they went to 5, they went to 6, they went back to 2, 3, 9, 8, 7, 6, 10, 3, and then back to 1. So I only use the edges. I did use the vertices more than once, but I only use the edge once. Okay, so it says which of the following contains a Eulerian circuit. So when you know if it's going to have a Eulerian circuit, they're all going to have an even degree. So straight away, what's the degree? This degree of this one is 1, isn't it? So I would then say, well, that's out because it has a degree of 1. Okay, if I look over here, this one, say here, it has a degree of 3. That already is an odd number, so I'm going to get rid of that one. If I look at, so look to see if someone has an odd degree. So down here, that's an odd, so it's out. And if I look at this, C looks like, C's correct. It has all even. So if we went through it, that was 2, that one's 4, that's 2, 4, 4, 2, and 2. So it's all even. So if I look for the odd one here, there's the odd one. So that one, there's an odd one, so it's out. Okay, looking at this one, to convert the network above to one that has a Eulerian circuit, we would add an edge between. So what you want to do is first find the degree of, so remember a Eulerian circuit needs even degrees. So if we go through, E has a degree of 3, A has a degree of 2, B has a degree of 4, C 2, and D is 3. So what if I drew an edge, what will make, edge between who will make them go to even? D and E. So if I drew an edge like that, this would then become 4, and this would become 4. So I can say D and E. So Hamilton trail. So remember, a trail is something where you can use a vertex. So the trail doesn't have repeated edges, but you use the vertices. But a Hamilton trail means you use all vertices. So if we wanted to, so we're gonna say Hamilton trail will use all vertices. Okay, so you just got to remember Euler is the edges one, the other one is going to be the vertices one. So a Hamilton trail, is using the vertices. So use every vertex only exactly once. It is important to note not all edges must be used. So you just have to get to every vertex, but you don't have to use every edge. So for their example here, they went to 2, to 3, to 5, to 4, to 1. And that's a Hamilton path or trail because it's done that. If you look other possibilities, so if I just did this one here, I could have gone 4 to 5, to 3, to 2, to 1. So there's many possibilities. There can only be 2 vertices with a degree of 1 with a dead end. In this case, these would be the start or the finishing. Okay, so that's the only thing. If you have if you had 2 degrees of 1, it means you'd get trapped out there. You can't come back out. So only one, otherwise they can be any degree. So the next one is a Hamilton cycle. So remember, a cycle will mean you start and finish at the same vertex, and Hamilton means we've got to use all vertices. So starts and finish at the same vertex, and we must use all vertices. So if we had a look here, we've got, so the only vertex you'll see listed twice when you write out your description of it will just be the first and last. So I'll only see E listed twice there, and all the letters in between, you should not see another double up. So that can be a quick way to find it. So if we go and practice this one, so if I went through it, E to A to C to D to B to F, and then we go back to E. So if we put our little arrows along what we did there, and you can see we start and finish. Okay, and so that's the only here, start and finish. All right, so down here, example 4, it says, for the graph above, which of the following is a Hamilton circuit? So what you got to remember, you go, okay, I've got a Hamilton. That means I can only use every vertex once. And because it's a circuit or cycle, I know they start using the words, but circuit, and well, in a Hamilton case, a Hamilton circuit or cycle just means you're going to hit the last one. The first and last will be the one you only use twice. And you only use, it doesn't matter about the edges, it's just the vertices. So if you go through, if you look at it, like I can just quickly look and see, all right, if I start at A, okay, so there are okay options. I'm going to get rid of this one because it doesn't end on the same one. Sorry. And then you shouldn't have repeated vertices. So if you look in, say, this bottom one, see, can you see how it repeats B twice? So I'm going to get rid of that because you can only use the vertex, only the start and finish one can be listed twice. So then if you look at the D, doesn't it list B twice as well? So I'm getting rid of that. Now let's have a look. So now really I only have to test 2 of them. So if I quickly go and test the top one, I went from A to B to C, and then it wants to D to E to F, and then it wants me to go back to A. There's no path there. So that one is not going to work. It didn't work. And so hopefully this is our answer. So if I do it, I'm going to do it with arrows. A to B to F to E to D to C and back to A. So I touched every vertex and I started and finished at the same one. So it's a Hamilton circuit or trail or cycle. All right. So, we've got another example. Example 5. So let's have a look. Which one of these has a Hamilton path? So a path means it just has to have every vertex only once. So I'm going to get rid of anything that's repeating. And I can see repeating, repeating, and also repeating. So once I quickly got that out, this top one is the only option for a Hamilton path because it doesn't. And if I have a double check, A, B, C, went to D, to E, F, G, and H. Yep. So there's now, I've used every vertex only once. So here's a little summary for you. So we go through. So remember, if you just remember Euclidean trails, or the E for edges, yeah? So the E ones are the edges, to do with edges. And when it's Eulerian, it just means every edge has to get used. And then for the Hamilton, obviously, they're the vertices. And it just means if you've got a path, every vertex has to be used. And if you have a cycle, it's every vertex has to be used, but except to the start and the finish, you've got to be at the same one, all right? But there's all those things. The Eulerian trail, just remember you can have exactly everything, or 2 vertices that are odd and everything's even, or things like that. All right, a circuit, Eulerian circuit, all have to be even. Where does that? All even. So little tricks like that is going to make you quicker.